ladies and gentlemen, is none other than Professor Dr. Michael Clancy. He is currently the director of Tanyapura Integrative Health Center, as well as the honorary president of the European Society of Anti-Aging Medicine, ESAM. Professor Clancy has got a very long CV, but he started off way back in Munich and became a professor in psychiatry, psychotherapy, as well as endocrinology and dermatology. He then was responsible for the opening of the Clancy Institute for Anti-Aging in Munich as well, where he was the medical director. In about 2007, he was given the professorship of various universities, among them the Udayana University in Denpasar, as well as Mei Fah Luang University in Bangkok. And he is also an honorary professor at UCSI, which is a private university in Kuala Lumpur. Ladies and gentlemen, I present to you Professor Michael Clancy. His topic for today will be stem cell therapy, a new way to eternal life. Professor Clancy.
Thank you very much. Thank you very much for the nice introduction. Dear distinguished colleagues, I'm very happy that you all came, and be sure we know to value your attendance here, and we hope you will enjoy this 3 days or 2.5 days in new anti-aging science. When we talk about lifetime, we should talk about stem cells as well, and I think one of the main topics here is stem cell treatment, and the question is really, what is stem cell eternal life? You see, there's a lot of confusion in stem cells. So what I hear about stem cells, these are doing this, there are embryonic stem cells, there are iPS cells, adult stem cells, mesenchymal stem cells. So what is it? What is helping you? What is doing? So the question is actually, when we're talking about eternal life, are we staying young and living forever? Is it a dream who becomes true for the next time already starting? So let me give you some overview about what is so important when we talk about stem cells. I don't prefer any method, just I want to tell you what is important. In stem cells, we have 3 major types of stem cells, which are embryonic stem cells, which they come from embryos that develop eggs that have been fertilized in vitro. They are not derived from eggs fertilized in a woman's body. Induced pluripotent stem cells and iPS cells, they are made by introduction of retrovirus, which is loaded probably with some genes, which are embryonic genes, and so adult stem cells, let's say from the skin, the fibroblast, is demethylated and from its hypermethylation stage, and the embryonic gene starts to work again. That's another method. So there are many methods how you can produce iPS cells. And we have the adult stem cells. The adult stem cells, all of us have. We have a lot of stem cells, and we produce every minute millions of stem cells, everybody of us, and that's why it's important. They are undifferentiated cells, and they are in the tissues and organs. They live in some parts which are called niches, and they have multipotencies. That's the way the nature works. From the single cell embryo, which has a totipotency, can become any kind of stem cells, to the pluripotent cells, which are almost any kind of embryonic stem cells, and the multipotent, which are more the adult stem cells, where we have cord blood cells, fetal cells, placental stem cells, and the adult stem cells, which we have mesenchymal or hematopoietic stem cells. So this is actually the order. Actually, on the other side, it's a life journey. It's a life journey from the embryonic stem cells. And all our stem cells, what we have, they come from embryonic stem cells. The origin, even the adult stem cells. Let me show you shortly induced pluripotency cells. What we're doing there is genetic reprogramming. That means we reprogram the cell, bringing an adult cell back to an embryonic cell and use them And fortunately, you know that the Nobel Prize was given to Japanese and American researchers last year for this work, great work. But at the end of the day, what happened is we cannot use it right now really in a clinical way because especially the retrovirus is not easy to control when we give it to a patient. But we have our adult stem cells, and they are everywhere. They're in the skin, in the breast, in the surface, in the testicles, in muscles, in bone marrow, and they can do a lot of things. They can treat stroke, traumatic brain injury, Alzheimer's disease, deafness, bone marrow transplant. This was the first actually would become a treatment with stem cells, and even diabetes and Crohn's disease. Here you see the development, which is important to see the development from the hematopoietic stem cells via progenitor cells. The progenitor cells are already committed to become this one. And for this to be committed, they need commitment factors. So this is a very important point. If there's no commitment factors, they don't know what to do. And the same as with other tissue stem cells, neural stem cells will live in the brain, or mesenchymal stem cells in fat, skin, bone, cartilage, and so on. What makes stem cells grow, differentiate, and find the way they have to go? This is the most important question. You can easily take stem cells out, make a biopsy, fat or whatever, skin, give it back, but you don't know the destiny of your cells. Where they go, what are they doing? And how can you control the way where you want to go? Let's say you have a patient with Alzheimer's disease or you have an aesthetic patient. So the one who goes to the skin, how can I manage the way that it goes to the skin or it goes to the brain or whatever you want to have? So right now we have to know that undifferentiated cells have the rise to all body cells. That we know. They have a self-renewal. This is a cloning way of self-renewal and multipotency. And what is very important, they need factors responsible for cell differentiation and factors responsible for the maintenance of a pool of progenitor cells. If you do not have factors who maintain the pool, you lose the pool and you don't have any stem cells anymore, so it cannot be. But we have, and when we treating patients with stem cells, we have always take in consideration that we need this. The pool maintenance or differentiation is, here you see the self-renewal with cloning, and this is the differentiation. And if you see here, this is the membrane, and the reason why cells stay still in the membrane, in the niche of a brain or skin or whatever, is that there are some factors which keep them staying, and there are other factors which keep them in the way to divide and differentiate. So cell division, actually if you have one cell, you've got two progenitor cells. From two progenitor cells, you've got two for the pool and two for the differentiation, and so on and so on. And then the progenitor cells, they're waiting here to go to the place where it's an apoptosis. But the apoptosis alone is not signaling. You know, you can have the following. You can have a cut here, and if you have a cut here, what happens? It becomes a scar. Why does it become a scar? Because the signaling between one side, they're all over stem cells in the skin, but the signaling is not ready. There's no commitment factor. There's no signaling. So what becomes a stem cell when you do nothing? When you just put out a stem cell, put it on a layer, so it becomes a fibroblast. So that's why it becomes a scar. It produces connective tissue. So when you want to have skin, you have to do something to build it up. And you have to know which stem cells you have. You know, you need to know the surface markers of the stem cells to give you the information which kind of stem cells are the ones who are important in the healing for which organ. Stem cells have a home, and the home is a stem cell niche. And that's where they live. It's a microenvironment around the stem cell, which is extremely important. And this keeps them in the microenvironment, as I showed you, or that gives them out. They have direct contact, or they are with soluble factors, or they have a connection to intermediate cells. Here, an example where you have a lot of stem cells. You know the old story when I was young. They told me every day we lose our neurons, every day we lose brain mass, and at the end of the day we are going to be stupid. So that's not true, because our brain has, especially in the close to the hippocampus area here, in the third ventricular layer of progenitor cells, which are waiting to repair if something happened. But if there are not enough factors, hormones, minerals, or whatever, vitamins, and other growth factors, which can tell them that they should go there and they should repair, you can do what you want. You can inject stem cells how much you want, you will never get a result. So stem cells alone can do actually nothing. So that's why stem cells need an environment to divide and differentiate. They need first inflammation, cytokines, TNF-alpha, interleukin 6, and interleukin 1. If they have anti-inflammatory situation, it stops the whole process. They need growth factors. They need myelin for the neurons, myelin progenitor factors. They need other growth factors and hormones. Growth hormone, testosterone, estrogen. Estrogens are very important in this way. So at the end of the day, we need a signaling that the stem cells come out. For example, hematopoietic stem cells, they have this signaling, this angiopoietin 1. So this is a very important part to come out of the niche and go to the place. So how do we get the stem cells out? The stem cells, actually, it is very simple. They're waiting for a trauma. If you don't have a trauma, if you are 16 years old, you're very healthy, and I give you stem cells, nothing will happen. Nothing. Just go out. The problem is you need a trauma, you need a wound, you need a chronic inflammation. Then they can start to signal, and they need the real microenvironment. You see here, this is a picture which shows very good. There's a signaling for the stem cells going there, which is inflammation. At the end comes to the wound healing. We told this, how get we the stem cells to the crime scene? So there's a journey of stem cells in the body all the time, all the time. Our body is a bioreactor. If we have our, good PhDs and people who work in the laboratories in biotechnology, and they do make organs, disc or heart valves or whatever, outside of the body, they use a bioreactor. They use mechanical stress. They use everything, hypoxia and so on, to bring the cell to that point in a 3D scaffold to become an organ or whatever. But our body does it on themselves. So what is the secret behind this? The secret are the microenvironment. So to create a microenvironment, we need all the cytokines, hormone messenger, growth factors, amino acids, vitamin, minerals, and so on. I'll show you one example. You have here stem cells come under a microenvironment with growth factors, FGF, EGF, VEGF, and then they would divide, but the differentiation of the cell division is done by P21, which is an apoptic molecule, which stops the cell division and brings the cell into differentiation, so that at the end of the day, is a sprouting protein. So this is something only one. Another one is in multiple sclerosis, there's this demyelination of the nerve axon, and there we have the leukemia inhibiting factor. He stimulates this, and with many different in between, like BCL2 and BCLX, it becomes, and even with the inflammation, it becomes the new myelin sheet. We have here a first sample of a patient without growth factors, culture 7 days without growth factors, and with growth factors you see there's a big difference in the cell division and in the numbers of stem cells, as well in the homing. So we learn everything for wound healing. What if you have a wound? Actually, we have a fibroblast migration recruitment. So recruitment factor, what is that? Recruitment factor is the inflammation, for example. Then we need a commitment factor who says that the the progenitor cell should become a skin cell or whatever, but normally it becomes just only a fibroblast, and we are happy when we have a neoangiogenesis. Here, a picture from a brain injury. You see, this is a normal brain here, and this is a brain injury. There's a big defect here on this side, and if you see that treating with stem cells, you know, is covering the defect more or less not bad, but if they have the factors, brain factors, especially brain factors involved, this is much more, and after 6 days it becomes nearly a closure of this. So it's actually a very important picture. This is a picture from my friend Kizela from Moscow. You know, see, they're making neural cell lineages with growth factors, at least, needs always these special factors. If you don't have them, you must not even try with stem cells, actually. Mechanical stress, as I told you, is important. Shaking, whatever. Hypoxia is important for some, especially angiogenesis. So at the end, like Albert Einstein said, everything should be made as simple as possible, but not simpler. So we have to see. What is the result? I have put some results from some clinics here, not my own results, because we are just working on this, so it's not ready for public. You see here, this is diabetes type 2. Diabetes type 2, this is the actual center in Cologne. And you see that diabetes type 2 has a strong improvement, 10 from 23 patients in this 6 months. This is a good sign. We have heart renovation. You know that normally the heart, if after myocardial infarction you have a reduced pump function, reduced ejection fraction, so they use catheter, the cardiologist, and inject the stem cells into this area, and you get, for sure, improved situation. This is the study trial, randomized trials. You see very good with improved left ventricular ejection fraction and so on, compared with placebo group with non-treated one or whatever. So this is actually a huge, huge, huge way for longevity and for life extension. And you see here the ALS, which is a disease, amyotrophic lateral sclerosis, Lou Gehrig disease, actually a disease which you cannot do anything. Right now they do, and you know, they die anyway. So what happened? We have even one patient with strong improvement and improvement 90 patient, which is very good here in this way, and stroke, which is very interesting as well to treat as well. Spinal cord injury, this is one picture from St. Pudick's in Bangalore in India. They have very important, strong results with mesenchymal cells, bladder movement restored, bowel movement restored, sensation on both of the limbs. If this is only restored, the patient is extremely happy. You know, must understand he can control the bladder movement and the bowel movement, and finally can walk with calipers. And this is the improvement of the spinal cord injury. You see that in every symptom there are improvements to find. Last but not least, the aesthetic, ladies and gentlemen, dear colleagues. And this is something which will be very interesting, because everything what comes in with the wound healing has something to do with the skin. And I can only invite you to see in our booth later, Professor Bader speak about the novel stem technique in cardiology in our lunch workshop as well, and Professor Trescaris about melatonin in the anti-aging field at the next break what we have. Thank you very much for your attendance.